As you can tell from my last name, I'm not going to be speaking in Polish. This is going to be completely in English. So what is 802.1aq and why does this matter to us and why should it matter to you? Today, if you're building a native Ethernet network, you essentially have three choices for control protocols. You have a spanning tree protocol that you can use a ring-based protocol, or you can use one of the lag or split lag type protocols. This work is aimed at addressing some of the issues and concerns with these protocols and giving us a new method going forward. So what I'm going to do is, this is the outline that I'm proposing, and it's fairly tight. I'm going to go through the requirements and the challenges and what led us to this protocol. I'm going to tell you what 802.1aq is. I'm going to give you a very brief overview of some of the applications, tell you a little bit about how it works, and then I'll give you a bit of a status where we are with the standards and so forth. And then if the internet and 3G card here works, I'll give you a very brief demonstration. Also, I understand there's going to be some questions at the end here, so if you pay attention, I'll ask some questions and we have some prizes. So in terms of the requirements, what were we trying to accomplish with this protocol? Well, obviously we wanted to get a larger scale. We wanted to get up to about 1,000 bridges. We wanted to be able to use all of the mesh. So if you build a topology that includes a lot of links, you should be able to use all of those links. We wanted to be able to use all of the paths that were available. So if there were multiple shortest paths in the network, we wanted to be able to use them all. And we wanted to be able to do efficient broadcast and multicast in the network. One of the big issues with Ethernet, of course, is the address learning. If we have to learn lots of addresses in core devices, it's a challenge. So we wanted to avoid this. And we wanted to do all of this with recovery times in the certainly sub-second or hundreds of millisecond time for larger topologies. We wanted to do this without looping, obviously, and we wanted to be able to create logical layer 2 topologies, and to be able to do this with far more than the 4,000 VLANs that were available. We wanted to increase that scale substantially. And to do this while maintaining the existing properties of Ethernet, the packet ordering, the symmetry of routing, the congruence, and to do this on a shortest path, which is a non-trivial thing to do. And then, of course, we had all the Ethernet 802.1ag and other OANM protocols that we really couldn't invalidate with a new standard. Probably the easiest way to understand some of these issues, and probably this is fairly simple stuff for some of you folks that have worked with spanning tree before. Here's an example of a 36-node spanning tree network. The green links represent physical links in the network, and the pink or purple, depending on the color there, represents the actual spanning tree, and you can see the root node off to the left. And one of the first things that we notice with this protocol is that I can't use many of the links in this network. Any link which is not part of the spanning tree cannot actually be used to carry traffic. So there's a lot of unused connectivity in this network. Next issue that I see has to do with routing. If I have a source and a destination down here, I don't know if you can see my mouse, down here a source and a destination, then I wind up having to go all the way up and down this tree. I wind up having to go up all the way up and down this tree in order to get from my source to my destination. And then finally, I may have hundreds or thousands or tens of thousands of addresses out here that have to be learned all the way up and down the tree. So that puts a heavy burden on these core devices, these devices in the middle of this network. So these are three examples of issues that were being addressed. So what is shortest path bridging, and how does it do this? Well, the first thing is that this protocol builds on top of the existing 802.1 standards. It's not inventing anything new where it doesn't need to. It's essentially just a new control plane, and it's a control plane for the two existing data paths, the Q and Q, and the MAC and MAC data path. The Q and Q mode of shortest path bridging is referred to as SPBV, and the MAC and MAC mode is referred to as SPBM. I'm going to be talking pretty much exclusively about SPBM. It's the one that I'm most familiar with and the one that I have implemented in my lab and the one that I'm going to be showing you. The protocol is completely backward compatible with all the existing 802.1 work, 802.1ag, and the various data center bridging initiatives in IEEE. Provides multiple loop-free shortest path routing, So it makes very good use of the entire mesh. And currently it supports 16 shortest paths from any given source to any given destination, but there's work ongoing in future for even more paths. The multicast mechanism supported, there is a head-end multicast mechanism similar to VPLS, and a tandem multicast replication model, which is, of course, very similar to what currently happens with Ethernet. One of the most interesting aspects of this protocol, and if you haven't encountered this before, it's quite powerful, is the ability to do a form of lightweight traffic engineering. Because the protocol produces deterministic routes from a source to a destination, and an offline tool can very easily tell you exactly what route will be used for any given service, it's possible with an offline tool to place the traffic exactly where you want it. This is not easy to do with a protocol like IP or protocols that hash along the way. This protocol will scale to about 1,000 or so devices. We use the ISIS link state protocol, which of course has already been used in scales well beyond that. And so this is, represents a huge improvement over the spanning tree protocols and scales. Convergent times, in our labs, we're definitely seeing sub-second, usually on the order of a couple hundreds of milliseconds of recovery time. That's actual end-to-end outage. And one of the live deployments from another vendor was showing something like 300 millisecond recovery times with 50-odd nodes. So very good convergence time, certainly better than STP in many instances. Again, this protocol is the ISIS link state protocol being used. And one of the things that we do here is we just simply add to the ISIS protocol. We're not saying that ISIS has to be used by itself. You can use ISIS with IPv4 or IPv6. You can use the multi-topology features of ISIS. All of these things can operate in parallel with shortest path bridging within one ISIS instance. So it's a very flexible arrangement. You don't have to run multiple things. The ISIS protocol is used not just for topology discovery, but it's also used to advertise membership information. Membership information, I mean the ports or the logical ports that you wish bridged together in this network. So you go around the edge of the network indicating which ports are to be bridged, and ISIS will advertise that. And the rest is then done through a computation. So as I mentioned, there's no address learning in the core of the network. The address learning is restricted strictly to the edge of the network, where we learn the relationship between a host and a box MAC or a MAC address of the device which can reach that end host. We do that through encapsulation with MAC and MAC. The inner addresses, or sorry, the outer address, the box MAC addresses, are never learned. They are simply computed and populated the same way that you would with a router. And I'll talk about that in a little bit. The unicast and multicast is handled at the same time. We compute unicast routes, we compute multicast routes all at the same time and pop them into a forwarding table and away you go. What makes this all special is the calculations. So the calculations are designed to produce symmetric routes. So you get the same behavior that you would with an existing Ethernet network. The unicast and multicast are congruent, so they follow the same path. And then, as I said, you have 16 different equal cost paths that you can play with to tune and adjust the traffic patterns in your network. So this little picture gives you a very high-level view of what SPDM does. Assume a network of hundreds and hundreds of switches running SPDM. And I wish to bridge arbitrary ports in this network, logical ports anywhere in this network to anywhere else in this network. Well, I assign an ISID, a service identifier, to that set of ports. And then I configure that ISID strictly at the edges. So I go around, this is the only configuration step you have to do, configure at the edges of this network that I wish those ports to be bridged, and they will be bridged logically. I can have 2 ports in an ISID. I can have more ports. I can adjust. I can add and remove ports. Take my two port one here and add a 3rd port to it, add a 4th port to it. It's all dynamic. You assign an ISID, you go around the edge of the network, assign the logical ports to those bridges, and it just all happens by computation. As I said, this is done with a service identifier or an ISID, so we got many more than the 12-bit VLAN ID. We've actually got a 24-bit service identifier to isolate these layer 2 networks, logical layer 2 networks within the physical network. In terms of the edge learning, once we've actually produced a tree, and this little picture here represents the same 36 node network I showed you before, where I've got 8 nodes that are terminating a particular service, a particular ISID 255, and I'm bridging this device A on the lower left to the device and device B on the upper right, and I'm not showing anything else connected to these other attachment points here. A spanning tree, a broadcast tree has been produced from node 1 to reach exactly the other members of this set, and the learning proceeds as follows. First, before we do any learning, we point out that the core of the network doesn't have to do any learning. Okay, so node 20 here knows how to reach node 1, it's this way, and it knows how to reach node 22 knows how to reach node 20, it's this way, and it knows how to reach node 1, it's this way. It has a forwarding table already pre-computed with the box max of this device and this device. So our host, A, sends a message to node B, doesn't know where node B is. It arrives at the uniport. The uniport doesn't know the relationship, so it broadcasts it only to the members of this ISID. So there's no learning of the multicast tree here either. It's pre-computed. The packets go exactly where they need to go. Eventually, we reach an edge. The edge now learns that host A is reachable via box B, box MAC 1. Okay, so we now know that it's come from 1. And B eventually replies. And when B replies, it now knows, this node here, 20, knows how to reach node 1. We know where this host A is. We can find it in this local learning table here. A is via 1, so we can unicast it back to 1. And then likewise, we learn the inverse relationship at the other end. Now we know B is via 20, and this is what the actual data path encapsulation looks like. You have the outer CMAC, which is just the normal 802.1 style header. And then we have in the core of the network, we have what looks like another copy of this. It's the so-called MAC in MAC. This is the outer MAC that the routing is done on in the core here. These are the box MACs, the source and the destination box MAC, a BVLAN, and then the ISID that identifies the service locally here. In terms of ECMP, or equal cost multipath, this is the network that I showed you previously, and I'm showing you all the different source destination pairs around the periphery of this network, and I'm showing you the actual 16 shortest paths that are available all at the same time. And so you can, at the edge of this network, assign your traffic to any one of these deterministically. So what are the sorts of applications for this protocol? Well, anywhere that you're using spanning tree today, obviously you can replace a spanning tree network with a shortest path bridge network. Metro Ethernet, VPLS, of course, is very popular in a Metro Ethernet environment, and essentially what we're doing here is somewhat equivalent to what VPLS does. It's a very lightweight form of VPLS because, as you can see, there's really only one configuration step. So it's a much lower OpEx solution than VPLS. Wireless backhaul, the layer 2 VPN is one of the deployment models for LTE. So shortest path bridging could be used for an LTE deployment. And then, of course, one of the most interesting ones is the data center / cloud. Some of the requirements that are coming up now in the data center are to treat the network as one big L2 switch by combining hundreds or even thousands of smaller switches into a non-blocking topology. Essentially, this allows us to place any server anywhere we want. We can put the routers. Anywhere we want. We can put the servers anywhere we want. We can put appliances anywhere we want around the edge of this network. And most importantly, any virtual machine can run anywhere in this network, and its IP address doesn't have to change. This is one of the key requirements for virtual machine migration or non-interrupted virtual machine migration. The topology allows for minimal congestion and flexibility in how the power is used. So shortest path bridging in this context has a number of advantages. The shortest path routing, of course, allows us to go across the bottom of one of these topologies. I can very efficiently go across this topology, and if I'm sending traffic from one server to another server, I can go shortest path between the two. It actually turns out that something like 70% of the traffic in a data center is between servers as opposed to coming in and out of the data center. So horizontal shortest path routing in that context is very important. The multiple shortest paths allows us to use 2 or 3 uplinks. If my server has 2 or 3 or 4 or even more uplinks, even up to 16 uplinks into the fabric, I can use all 16 of those, and I'll show you a little example of that in a minute. The address isolation through MAC and MAC means that these core devices don't have to learn all of the end station addresses. And then, of course, the other attributes, fast recovery and non-looping, are, of course, desirable attributes as well. Here's a couple of subnets. In a data center, the L2 VPN corresponds to an IP subnet. So just being able to flexibly add and remove subnets and grow and shrink them, very easy to do. As I said before, the protocol really is completely transparent to things like VMware. So any layer 2 protocol that normally operates in a data center will operate transparently over top of shortest path bridging. And again, fully compatible with all the load balancer type applications and appliances out there. Virtual router redundancy protocol, it's again transparent to VRRP. And as we go forward with new inter-DC connectivity protocols, that should be relatively transparent to shortest path bridging as well. Here's just a little example. This is from one of our network emulators showing a fat tree with 16 spine nodes and then a number of nodes, each 16 ways connected into that spine. And this is actually showing 16 different shortest paths available to shortest path bridging through this network. So you can take a service and assign, service 1000 could be assigned to this route, service 2000 could be assigned to this, service 3000 to this, and you could spread them around any way you want. Or you could let the system just spread them. This is the multicast spreading, showing one of 16 different paths for the multicast. And it's in this particular case, this service is using this node here as its replication point. But again, the services can be assigned to use different replication points here, or you can just let the system pick it. It's a very controllable protocol. So how does this protocol work? Well, from your perspective, from the operator's perspective, it's designed to be very easy to use. You basically plug the network to network interfaces together, and they come up. And then you go around the network, grouping the ports, logical or physical ports that you wish to be bridged together. You assign a service identifier to them, and that's it. The network comes up, the services are bridged, and at that point you have the 802.1aq OANM that you can use to figure out what's going on and debug and so forth. And if anything fails, of course, the network will automatically restore connectivity. So externally, it's very easy. Internally, what goes on is a little more complicated, of course. The ISIS protocol initially reads the box MAC. So when you buy the box from us or anybody else, it comes with a MAC address burned into it. That box MAC address becomes the address of the device as far as the routing is concerned. And it's advertised by ISIS. So you don't have to configure it. The ISIS then looks at what uniports you have assigned to what services and then advertises the set of services that it wishes to receive. And then every node in the network takes the full topology and the list of services and runs it through a computation, and the output of which are forwarding tables that bridge the set of ports that you requested along the routes that you requested. The data path, when a packet arrives at the edge of the network, It's obviously got a CVLAN, SVLAN, or it's untagged, arrives at a uniport. And then based on either the double tagging, the single tagging, or no tagging, the packet is assigned to a particular service. It's encapsulated with the box MAC of the source bridge. It's encapsulated with that ISID. It's associated with the logical port that it came in on. And then it's assigned a BVID, which determines the route that it's going to follow across the network. And you can either manually assign that, or you can let the system assign it. Finally, the destination, the box destination MAC has to be found. And if we know the local host address, if we found it before, then we know what box destination MAC to use, and we encapsulate it unicast, and off it goes. If we don't, it goes multicast to all of the other members just of that ISID. It only goes to other members of that ISID. The Tandem nodes, well, it looks a lot like IP at the Tandem nodes. You compute the shortest path from yourself to all of the other nodes in the network, and the address that you install is the box MAC of all of those other nodes. And that goes into your forwarding table. That's repeated 16 times. It's not really repeated 16 times, but logically it's repeated 16 times to give you 16 different shortest paths to all of the other destinations, and each one is assigned a different BVID. And then there are some special tricks that are played with the computations that assure the symmetry and congruence of the unicast and multicast routing. It's probably best to understand just by looking at a little diagram. Here we see a 6-node network. Node 1 and node 4 are the nodes that we're interested in. There are 4 different shortest paths available, assuming that these are all equal cost paths, from node 1 to 4 and node 4 to 1. Well, node 1 has a forwarding table that essentially says to get to node 4, I can go out interface 9 and use BVID 1. I can go out interface 9, use BVID 2, or interface 10 using BVID 3, interface 10 and BVID 4. And so I have these 4 different paths here. Likewise, on the other side, I get the inverse, hence the symmetry. And if I were to look at the forwarding table on node 2, for example, it would show a corresponding BVID for this yellow going out this interface here, as opposed to any other interface. So it's fully deterministic. The set of forwarding tables produced are fully deterministic. In terms of OANM, essentially everything that's in AG is available. So the continuity check, loopback, traceroute, various other attributes, some of the 1731 stuff, all works. Really anything that's designed to work with Ethernet will work with this protocol. We haven't broken anything. We also haven't explicitly added anything either. It's completely backward compatible. So there are thousands and thousands of man-years of effort that have gone into Ethernet OANM, which has been preserved here. So let me quickly give you an update where we are in terms of the status of this protocol. Currently, there are about 20 live deployments, some small carrier, some enterprise, large enterprise, and some DC fabric has been deployed. In terms of the data path, the PBB data path, of course, that's very widely deployed in lots of environments, and the Ethernet OANM has a massive worldwide deployment. So the control plane is already starting to see some activity. In terms of interworking events, interoperability tests, we've actually conducted 3 interoperability tests. I've conducted 3, 2 in my lab and 1 in somebody else's lab. And I'll talk a little bit about that in a second. Trials, there have been, from my own perspective, there have been a couple of service provider trials. I can't tell you what some of the other vendors have been doing. In terms of the standards, shortest path bridging has 2 components. It has an IETF component and an IEEE component. The IETF component is complete. The RFC is sitting there waiting. And the IEEE component, they're in sponsor ballot. They're meeting in Hawaii next week to finish the ratification. So this should all be wrapped up and complete within a month. We're actually now looking at version 2.0, sort of continuation on with this work. What can we do next? One of the highlights here is 802.1q, which is work that just started last year. which adds hop-by-hop hash DCMP, similar to IP. So you'll have a choice between what type of forwarding mode you want to use with the future versions of 802.1aq. And something which is very interesting, I find, is this new work called, it's a layer 3 VPN. It's called Shortcuts. And what it does is it allows us to run IP over top of the SPB BMAC layer, and in a way similar that you can run IP VPNs and L2 VPNs on MPLS with one infrastructure. You can run L2 VPNs and L3 VPNs on top of a BMAC routed layer and one protocol, ISIS. So this is new work that's just starting. I'll just talk very briefly about one of the most recent interop events. This one was done, involved 5 different vendors, my own company, Alcatel, Avaya, Spirent, and Solana. And we set up a 10-node physical network, like this mesh you see at the bottom, a bit like a data center non-blocking fabric. Spirent injected 180 some odd nodes, 170 some odd nodes into here. And then we ran data across the bottom from various services to other services and tested out the protocol. And we had our problems, but for the most part, we were able to get this to work. And it was actually quite successful. That picture on the left there is one of the OANM systems that listens to the ISIS protocol and then draws the SPB picture, as opposed to having to run SNMP to each of the devices. This is one of the trials. There's just a couple of pictures from one of the service provider trials. This was a demonstration of a core network emulation replacing VPLS. And so we took a 100 and some odd node network and 5 physical devices and emulated a real service provider topology running SPB instead of VPLS. Okay, so now assuming that my internet connection is still working, and we will see if it is. Yes, it is. Okay. What I'm going to do, how much time do I have left here? Okay. What I'm going to do is I'm going to demonstrate a small network. I have 5 physical nodes, and then in addition to these, 4 physical nodes, and in addition to these 4 physical nodes, I have a Spirent, and the Spirent is injecting 100 odd nodes into this topology. I then have 2 hosts, and these 2 hosts are simply on the same service, on the same ISID, and they're just pinging each other. They're just little laptops. So we've configured a particular ISID here, ISID 1000. We've configured ISID 1000 here. That's really the only configuration step we've done in terms of the services. And the network is automatically bridging from this port to this port. I know that's kind of a boring example, but it's a little hard to show something much more complicated in an environment like this. We're going to telnet into this node 1, and I'm just going to show you a few commands here so you can see what's actually going on. Now the trick is going to be to do this and hold the microphone at the same time. All right. So if I speak loud, can you guys hear me if I speak loud? Or does somebody want to hold the microphone for me while I type? Sorry about that. All right. So we can look at the SPB status here. Here we're looking. We can talk. This is the MAC address that's been assigned to this device, and we're using 2 VLANs, 40 and 41, for all of the nodes in this network. This is just a quick status. Gives us an overview of some of the numbers in the network. So we're running the MAC in MAC mode. We've got 106 nodes, lots of links, and so forth. This is the ISIS peering. Oops. There we go. And we're seeing 2 of the physical nodes adjacent, and then this node here on interface 20 is actually one of our emulated nodes. So if we look back at the picture here, we're looking at the adjacencies, so we can see these 2 network-to-network adjacencies here, and then we can see the emulated adjacency here. Okay, so now if we look at the link state database, the ISIS LSDB, stuff in it, and these are all the emulated nodes that we're looking at. And as we list, we should see the link state entries for our 4 physical nodes, and the star means that this is our own link state entry. Okay. Next thing we're going to do is we're going to take a look at the 2 equal cost shortest path routes from node 1. So I'm just going to look at node 1 and ask it what's the route to node 5. And I'm going to start by showing the FIB, the unicast forwarding table. And we'll see there are 2 entries for this node 5, whose box MAC is S9305. So we'll do that. So these are the unicast routing table. And I have to sort of stop this at the right point. And we'll see the S93035. Here it is. Here's my S93035. And I can see the 2 ECMP entries. So one for BVID40, one for BVID41, and one going out interface 19 on card 2, the other going out interface 18 on card 2. And that, if you look back at the picture here, this is exactly what we're looking at here. Right? These 2 interfaces here. Okay. Well, next thing I'll do is I'll ask the device, this switch, what's its route to node 5 using VLAN 40, and what's its route to node 5 using VLAN 40. And then we'll do the same thing using the trace route, or the MAC, the trace MAC. If I could type. There we go. So that's the computed route. And here's the computed route to 41. And there's the 802.1aq trace from ourselves to node 5 using VLAN 40, and we can see that it's gone through node 3. And I can do the same thing, 41. And it goes through node 2. And I can do ping MAC and all that other good stuff as well. So the last thing I'll do is I'm just going to show you some of the stuff that's been learned. And as I said, the only learning that occurs in this network is at the edge. So we'll just look very quickly at the local and remote learning that's happened on node 1. And so what we're going to see is on node 1, it's locally learned that this little host's MAC is via interface 21, and it will have remotely learned that this MAC address, this host MAC, is reachable via this device's box MAC or BMAC. And so I'll show you that. Oh, what's the command? So this, before I do that, this just shows me for a given ISID all of the attachment points in the network. So essentially I'm seeing all of the ends of a logical layer 2 network in this network. One locally and one remote. And then we'll take a look at the learning. This is the local table. So we see this one CMAC locally off interface 21. And then the remote. And we can see reachable via the box MAC of node 5. Oh, it worked. So that completes the demonstration and the overview. If you want to get more information about this protocol, probably the best place to go is Wikipedia. We've been trying very hard to keep the Wikipedia page up to date. And obviously you're more than welcome to send me an email or any one of the other folks involved in the protocol an email, and we'll be happy to try to answer your questions. Now, I understand we have some prizes for questions, so I'm going to ask 3 questions, and the person who gets the closest gets a prize. And I don't know where the prizes went, but sure, you're going to give them out. So I guess the first question is shortest path bridging uses something called an ISID. The ISID does the same job or a very similar job to a VLAN in MSTP or 802.1. The ISID is much bigger than the VLAN. The VLAN is 12 bits. How big is an ISID? 24 what? Oh, hey, answer form, yes, okay. Okay, very good. Second question, how many interoperability tests have we done? Yes. Who said 3 first? I believe the gentleman in the front said yes. And now I have to think of a third question. In the interoperability tests, within, say, 50 or so nodes, what was the largest network that we built? Yes? 10 physical nodes, that's correct. And it was 180 emulated nodes, correct. Oh, those are all too easy. And I'll end by asking if there are any questions. And if somebody wants to ask questions or see further demonstration or talk more about this afterwards, I'm here all day tomorrow, and I'd be happy to sit down and show you more about this cool new protocol. Anything? Yes, go ahead. Thank you.
How fast do you expect that we could see this working in products of many companies?
You can buy this today. There's at least one vendor selling this today.
Yeah, but how much time before it comes its presence as a standard in many vendors?
So there are two. So there's one selling it now. There's another one will be selling it shortly. And a third will be selling it probably within a year. Beyond that, you have to talk to the marketing guys about their exact dates and schedules.
Thank you.
I'm a research guy, so over here was it? No. Anybody else? Okay. Thank you very much.